Hello, my dear students. Today, we're going to tackle a very important topic from our Unit 11. That's the dual nature of radiation and matter. We're talking about electron emission. Don't worry, by the end of this session, you'll understand this concept so clearly, you'll be perfectly ready for your exams. Cello, let's begin.
Okay, let's start with a simple question. We've all seen lightning during a storm, right? That big flash of light in the sky. But have you ever stopped to wonder, what is it, really? What's actually happening at the physics level?
Well, that massive, powerful flash you see, it's a huge, real-world example of our topic today. You see, what's happening is that the electric field in the clouds becomes so incredibly strong that it literally rips electrons away from the air molecules. And those escaping electrons, that's the spark we call lightning. This basic process of electrons escaping from matter is what we call electron emission.
Now let's zoom in, way in. From that giant lightning in the sky to a simple piece of metal, maybe on your study table. Inside any metal, there are crores and crores of electrons, but they are not free to just leave and go wherever they want. No, they are held tightly inside by the powerful attractive force of the positive nuclei. It's like an invisible fence keeping them trapped. To make this bilkul simple to remember, let's use a nice analogy. Just imagine that the piece of metal is a huge prison, a jail. And all the free electrons inside, they are the prisoners. They can run around inside the prison grounds, but they can't get out because of the high prison walls. That's our attractive force.
So for any prisoner to escape, what do they need? They need energy, right? Enough energy to climb over that big prison wall. In physics, this minimum energy needed for an electron to escape has a special name. We call it the work function. We use the symbol W, or sometimes the Greek letter phi. So remember this. The work function is the absolute minimum energy an electron must have to just break free from the surface. It's the energy needed to climb that prison wall.
Okay, so if our electrons are prisoners in a metal prison, they need an escape plan. And in physics, we have three main escape routes. 3 different ways we can give an electron enough energy to break out of its metal prison.
So what are these 3 escape plans? First, we have thermionic emission. Here, the method is simple. We just heat the metal. As it gets hotter, the electron prisoners get more and more energy. They start moving around faster and faster until some of them get enough energy to jump right over the wall. Second, there's photoelectric emission. In this case, we shine light on the metal. You can think of particles of light, which we call photons, as tiny little hammers. They come in, hit the electron prisoners, and knock them clean over the wall. And the third method is field emission. Here, we apply a very, very strong external electric field. Now, in our analogy, what this does is it basically lowers one of the prison walls, making it much easier for the prisoners to just climb out.
Now, Beta, this is a perfect summary for your exam revision. For thermionic emission, the key is high temperature. For field emission, it's a strong electric field. But look carefully at photoelectric emission. The key factor isn't just any light or even bright light. It's light of a high frequency. This one little detail, it was so strange to scientists, it would eventually change everything we thought we knew about light itself. So make a star next to this table in your notes.
So we know the escape routes. Now let's understand the rules of escape a bit better by looking at the prison wall itself. The work function. The work function, W, is an energy, right? We measure it in a very tiny unit called the electron volt, or eV. It's perfect for the atomic scale. Now the most important thing to remember is this. The work function is like a fingerprint for a material. Every metal has its own unique work function. The height of the prison wall is different for different prisons. For example, look at sodium. Its work function is only 2.3 eV. That's an easy prison to escape from. But tungsten and platinum, they have much higher work functions. They are like high security prisons, very, very difficult for an electron to escape from. Theory is one thing, but to make this crystal clear, let's do a simple numerical example. This is exactly the kind of question you'll see in your board exams. Don't worry, the calculation is very, very simple.
Okay, here's the question. Imagine a single particle of UV light, a photon, comes in. It is carrying 6.21 eV of energy. It hits a piece of tungsten metal. Now, we just saw that the minimum escape energy, the work function for tungsten, is 4.5 eV. So the question is, can this photon free an electron? Does it have enough energy?
Let's just compare the numbers. The energy coming in from the photon hammer is 6.21 eV. The energy needed to climb the tungsten prison wall is 4.5 eV. So it's quite clear, isn't it? The incoming energy is more than the energy needed.
So the answer is a big yes. The electron will definitely be emitted.
The photon has more than enough energy to knock that electron right out of the metal. It's a successful prison break.
But wait, what happens to the leftover energy? In physics, energy can't just disappear. The photon came in with 6.21 eV, but only 4.5 eV was used up just for the escape. So what about the remaining 1.71 eV? Well, that extra energy is given directly to the electron, and it becomes the electron's speed, what we call its kinetic energy. So the electron doesn't just escape, it escapes and rushes away with some speed.
Okay, class, now for a very important section. Let's talk about a couple of common traps in the exam. These are the small mistakes that can quietly kill your marks, and you won't even realize it. Let's make sure you avoid them. The first big mistake is thinking that the work function is some universal constant, like the gravitational constant g or the speed of light c. It is not. Please remember our fingerprint analogy. The work function is a unique property of a material. The prison wall for sodium is different from the prison wall for platinum, so always check which metal is being talked about in the question.
Now this is the most common confusion point in this whole chapter, so listen carefully. A lot of students think that if you shine a brighter light, the electrons will come out faster with more kinetic energy. This is wrong. Think of it this way. Brighter light just means you are sending more photon hammers per second, but the power of each hammer is determined by the light's frequency. So brighter light means more electrons can get knocked out per second, but a higher frequency light is what gives each electron more speed after it escapes. So here's a simple line you can remember for the exam. Just think, frequency is the gate, intensity is the flow. The frequency of the light must be high enough to even open the gate for escape. Once the gate is open, then the intensity, or brightness, determines how many electrons can flow through per second.
All right, we've covered a lot today. Let's just quickly put all the key ideas together in a short summary and see where this topic takes us next. So why does all this matter? It's because everything we learned today, the idea of the work function, and especially those strange rules for light, this is the essential foundation for our next very important topic, which is a deep dive into the photoelectric effect itself. So you have already built the base today.
So what are the key takeaways for your exam? Number 1, electrons are trapped inside metals and need energy to get out. 2, this minimum escape energy is a property of the metal called the work function. 3, you can supply this energy in 3 ways: heat, light, or an electric field. And 4, the most important special rule: for light to cause emission, its frequency must be high enough to overcome the work function. And all of this leaves us with a really amazing question. We have seen that light can behave like a tiny, concentrated particle, like a little hammer knocking an electron out of its home. But from our previous chapters, we also know that light behaves like a wave. So, which is it? Is light a wave, or is it a particle? The answer to that question didn't just win a Nobel Prize. It completely broke classical physics and started the quantum revolution. We will dive into that mystery in our next explainer.